All right, we're going to finish up this chapter on applications of integration by looking at fluid pressure and fluid force. So the pressure of an object at some depth h in a liquid is W times h, where W is the weight of the fluid per unit volume, like I think we call it the specific weight of the volume. Think of it as like the density of a fluid. And then h is the depth. So if we have an object at some fixed depth, submerged in a fluid of weight W, we just multiply those two things and we get the pressure. The fluid force is what's going to be really interesting. Now, for an object, if you think of a submerged horizontal surface, right? If a surface is horizontal, submerged in a fluid, that means that all of that surface is at the same depth. It's perfectly even. And so finding the fluid force is fairly simple. You're going to take the pressure and you're multiply it by the area of that surface. Where things get interesting and what requires calculus is if we have a submerged vertical surface, because if the surface itself is vertical, right, they're at all different heights. They're at all different depths under, submerged in the fluid. And so in order to find the fluid force on a submerged vertical surface, we're going to evaluate this integral. So again, W is the specific weight of the fluid, and we're going to integrate from C to D. We're thinking about this as a depth, so we kind of naturally impose coordinate axes, and what's changing is y, the y coordinate, right, because they're at different depths. So we're integrating with respect to y. H of y, which is the depth at y, times L of y, the length at y, times dy. Now this really is just an application of the second formula, because what we do is, if you imagine, if we're looking at this submerged vertical surface here in the figure, we say let's take a little slice. That's the little red rectangle here. We're saying let's take a really small piece of this, and we're just it's going to be so small, we're just going to think of it as being all at the same depth. And the area is the length times delta y. So there's your area. And then your h of y is just the depth. And that's sort of what's indicated here in the figure. And we're going to integrate that from C to D to get the total fluid force on the submerged vertical plate, submerged vertical surface. So we're going to spend most of our time just looking at examples where we need to use this integral formula. So here we have a gate that's in the shape of an isosceles trapezoid. It's 8 feet across the top, 6 feet across the bottom. It's got a height of 5 feet. We want to know what is the fluid force against the gate if the top of the gate is 4 feet below the surface of the water. Now, we have to be careful about our units here. We'll note that they've given us distance units of feet, not metric units. So when we're working with feet, then water has a specific weight of 62.4 pounds per cubic foot. So that's the value of W in the integral. What we want to do now is set up this integral. So I'm going to just write out what the integral looks like here. Right, I'm just writing the formula from the previous page. So we're integrating from C to D, h of y times L of y dy. Now we're going to be able to kind of tie each of these pieces to the figure. We know the value of W, so that's pretty simple. But our first, trouble, I don't know if it's exactly trouble, but the first thing we need to do is impose a set of coordinate axes. In these, application problems, in nature, you don't look out and see coordinate axes there. It's up to us to impose a set of coordinate axes, and it's often a good idea to take advantage of symmetry when you do so. So I'm going to draw my coordinate axes. I'm going to draw them so they go straight down the middle, and I'm going to draw it so that the x-axis is at the surface of the water. So the y-axis goes right down the middle. And now that we have coordinate axes, we can kind of figure out what coordinates of some points are. For example, this point here at the bottom right, that's going to have an x-coordinate of 3. And a y-coordinate, let's see, it is a total of 9 feet below the surface, so that's a -9. This point up here will have an x-coordinate of 4, because it's half of the top width, and it's 4 feet below the surface. Now what we're going to do to kind of figure out our h of y and L of y is I'm just going to draw a rectangle. So this has a width of delta y. H of y is the vertical distance from the surface to the rectangle. The surface, because of where I drew the axes, the surface is at 0. And the y-coordinate at the rectangle is just y, right? I imagine that I stop at some arbitrary y-coordinate. So that gives us an h of y equal to -y. L of y is this length. And here's a reason why we really wanted to take advantage of symmetry. Because if I can find the x-coordinate of a point on the end of that rectangle, then L of y is just double that x-coordinate. So I want to figure out what is x in terms of y along this line. And we have 2 points on that line. We can certainly find the equation of this line. Alright, so our slope, that's fairly simple. y2 minus y1 over x2 minus x1. So I guess I'll pick the top point as my y2, as my point 2, so -4 plus 9 over 4 minus 3, and that gives me a slope of 5. I can get the equation of a line using the point slope form. Y minus y1 equals m times x minus x1. So y minus a -4, y plus 4 is equal to 5 times x minus 4. So there's an equation of the line. I want to actually solve it for x, right? Because then L of y is 2 times x, and I want to get that as an expression of y's, because we're going to be integrating with respect to y. Going to distribute the 5. Solve for 5x. 5x is y plus 24, and then dividing by 5, y is 1/5 y plus 24/5. And in fact, I'm actually going to write it slightly differently. I'm going to just keep the 1/5 outside. 1/5 times y plus 24. Now when we double it, L of y, which is 2x, is 2/5 times y plus 24. Alright, so we have the pieces we need to put into the integral. Let's go up here. I'm going to scroll back up. We know that h of y is -y. We know that L of y is 2/5 times y plus 24. So let's plug this stuff in. W is 62.4 minus y times 2/5 y plus 24 with respect to y. Now, the one thing missing from this integral are the limits. So those y limits, how far down I could push that green rectangle, how far up I could push that green rectangle. And we basically already found them when we found these coordinates. So the y limits are going to go from -9 to -4. Alright, I'm going to yank out some constant factors. I'm going to pull out the 2/5 and the negative. So 62.4 times a negative 2/5. Whoops, 62.4 times negative 2/5. Negative 2496. And we're integrating from -9 to 4. And then I'm going to take this factor of y and I'm going to distribute it. So I got y squared plus 24y. Now we know how to integrate this. That we've done the hard part. The hard part is usually setting up the integral, and that did take quite a bit of work. The integral itself is simple enough since it's a polynomial. Using the power rule. And now we can plug in our limits. Oh, that's a negative 4. Oops, that's a positive 1/3. 1/3 times negative 9 cubed is 12 times negative 9 squared. And now I'm gonna do a little shortcut here. I'm gonna take this expression here that we got after we integrated, and I'm gonna put that into my y1 editor on the calculator. Of course, I have to use x as my variable because that's what the calculator likes. But then I can have the calculator just evaluate it. So let's see, vars, y vars function y1 of -4, 512 over 3, and then I'll just plug in -9. $7.29. And now we got one more thing just to compute here. So -24.96 times 5/12 minus 729. That gives us 13,936. Now this is force. So, you know, our linear units were in feet, which is why we had a specific weight of 62.4 pounds per cubic foot, right? I had to make sure that the units in the specific weight matched up with the linear units. Your units for the force are going to match up with whatever the force units were in the specific weight. So for us, that's pounds. Okay. Oops. Well, let's do another one. Here we have the side of a tank in the shape of a semicircle of radius 2 feet. And this tank is going to be filled with water. So if the tank is full of water, we want to compute the fluid force exerted on the side of the tank. So again, it's up to us to impose coordinate axes. Now, you're allowed to draw the axes anywhere you want, but there's certain choices you can make that will make your work a lot easier than other choices. So I'm going to take advantage of symmetry again. I'm going to draw it so that the y-axis goes right down the middle. And I'm going to draw it so that the center of the top is right along the x-axis, and that's going to make the equation of this circle really easy. So again, let's see, I'm just going to really quickly jot down a couple things. It's full of water, and our linear units are in feet still, so W is 62.4 pounds per cubic foot. If we draw kind of a sample rectangle here, that has a delta y width. The height is, again, the surface of the water is at y equals 0, so h of y is 0 minus y, which means we have a negative y for h of y, just like the last one. And again, taking advantage of symmetry, we know that L of y is 2 times x. So if we can find at a given y coordinate, if we can get an expression for like this x coordinate over there, we just have to double it. So we need an equation for the circle. And because of where we drew the axes, the equation for the circle will be really simple. So it's a circle of radius 2, centered at the origin. And such a circle has an equation x squared plus y squared equals 2 squared, or 4. So x squared is 4 minus y squared. And the x-coordinate, at least the positive x-coordinate, is the positive square root of 4 minus y squared. And so L of y is just double that. Right, I think we have just about everything we need to put together this integral. So the force is W times the integral from c to d, h of y, L of y, dy. W is 62.4. H of y is negative y, and L of y is 2 times the square root 4 minus y squared. dy. Our limits. The y limits are going to start down here at the bottom of the circle up until the surface, so that's from -2 to 0. Now before integrating, a lot of the time you would see me just sort of yank out that factor of 2 and probably the negative. I'm going to leave them in. In fact, I'm going to rewrite it just slightly. This square root of 4 minus y squared, I'm going to write that as a 1/2 power. And then we have times -2y dy. Maybe you see where I'm going with this. Maybe you want to pause it and see if you could think about how you would integrate this before I kind of go ahead and explain what I'm going to do. This one can be done with a u substitution. It's not a polynomial. It's not just a polynomial like the other ones, but it will end up being just a nice power rule integral. So we're going to let u equal 4 minus y squared, and then du is negative 2y dy. So that's why I didn't take out the -2 factor. We actually want it as part of our du. So everything kind of fits nicely. We don't need to throw in any factors. This is going to turn into, when we write it with u's, u to the 1/2 du. And then I'm just going to find u limits. So when y is equal to -2, u is equal to 4 minus -2 squared. U is equal to 0. And when y is equal to 0, u is 4 minus 0 squared, or 4. So we're going to integrate from 0 to 4 for u limits. Using the power rule, we have 2/3 u to the 3/2 from 0 to 4. Now I'm going to yank out this 2/3, and I'm going to multiply it by the 62.4 that's already there. We get 41.6. Plugging in our limits, 4 to the 3/2 minus 0 to the 3/2. 0 to the 3/2 is 0. 4 to the 3/2 is the square root of 4 cubed, which is 2 cubed, or 8, and we're going to multiply that by 41.6. We get 332.8. And again, the units for this result are in pounds. Alright, let's do one more problem here to finish up this chapter. This looks like it'll take a bit of doing. Got a swimming pool that's 2 feet deep at one end, 10 feet deep at the other end, and it's 40 feet long and 30 feet wide with vertical sides. We want to find the force against one of the 40-foot sides, so that's like this side right here that we're looking at. I'm going to begin by just sort of drawing out the region kind of bigger. So it's 10 foot deep at one end, it's 2 feet deep at the other. I'm going to impose, the way I've started to draw it, I'm actually going to pose the origin so that it's right down here at this bottom corner of the pool. So this kind of slanted slope there goes from the origin up to this point. That point there. So there's the 2 feet deep at one end, 10 feet deep at the other. Now, when we think about how we find these fluid forces, we imagine drawing this horizontal rectangle. Now, if I drew this horizontal rectangle down here, the length is sort of determined in a different way than if I draw it up here, right? In the bottom part, and there's sort of, I'm going to just draw this as a dotted line, kind of dividing up these two regions of the side of the pool. In the bottom region, that length is really determined by the slanted line, that slope. In the top region, the length is constant at 40 feet. So we're going to have to attack this with two different integrals. And I think I'll just call the bottom region, I'm going to call this region 1. And I'll call this one region 2. Region 2, y goes from 8 to 10, right? So when we set up that integral, we'll integrate from 8 to 10. With region 1, y goes from 0 to 8. So for region 2, L of y is 40, right? That's the fixed at the top, that's the fixed distance. And h of y, the depth, is top minus bottom. Now in this case, in the other examples, we drew the axes so that the x-axis was at the surface of the water. We didn't do that this time. the surface of the water is at y equals 10. So top minus bottom is 10 minus y. And that's going to be the same for both regions, right? It's still, you know, the surface is still at 10, and we still imagine that we're kind of drawing that rectangle at an arbitrary y coordinate. So there's our 2. I'm going to also, I guess, put the R1 details over here. So y goes from 0 to 8. H of y is still 10 minus y. For L of y, though, the L of y is going to be given by the x-coordinate on that line. So this line right here it's a line that goes to the origin, so it's really simple. It's just slope times x. And the rise over run is 8 over 40, so that's 1/5. Y is equal to 1/5 x, and that means that x is 5y. So that is our L of y. Alright, I think we have everything we need. I guess we'll assume that, I don't know if it says, but I'm going to just assume that we're filling it with water. So W is still 62.4. Alright, so let's do the R1 region first. 62.4 times the integral. This is from 0 to 8. H of y is 10 minus y times 5y dy. And for R2, this force 62.4 integral, this is going from 8 to 10. H of y is 10 minus y times 40. L of y is 40 there, dy. Both of these integrals I think are fairly simple to compute. I'm going to take out the 5. I guess I'll start with the R1 integral first. I'm going to yank out that 5, and then I'm going to distribute this factor of y. So 62.4 times 5 is 312. And we're going to integrate 10y minus y squared with respect to y. And using the power rule, we get 5y squared minus 1/3 y cubed from 0 to 8. And we'll plug in our limits. And then when we plug in 0, we'll get 0 because everything has a factor of y in it. $312 times 5. Oops. $46,592. This will be pounds. So I'll call this F1, I guess, since it's for the R1 region. Over here we'll have F2, and now we'll just do this integral. I'm going to take out this factor of 40. 2,496 times the integral from 8 to 10 of 10 minus y. Integrating, we get 10y minus 1/2 y squared from 8 to 10. Plug in our limits. For this first one, I think we can kind of do that mentally. So we got 100 minus half of 100, that'll give us 50. And then this is 80 minus, let's see, 64, half of 64 is 32, so that'll be 48. Alright, so 2496 times 2 is 4,992 pounds. So that's the total force for the top region, and then we have already found the total force for the bottom region, and now there's one thing left to do, which is just put them together. And when you add them up, you'll get 51,584 pounds of force.